So, hello everyone. I welcome you all to the open discussion of AIATS plus phase 2. My name is Lakshya, your chemistry faculty. I've been dealing with the organic section of this paper. Okay. In this part, we will be discussing some of the most important part of organic. And what are they? They are basically aldehyde ketones, carboxylic acid, as well as alcohol phenol ethers, as well as amines. Okay, so let's back to the question number 1. And in this part, we will be not discussing only the question parts. Along with it, we will be develop our conceptual clarity or according as per to the whole content. Okay, let's move to the question number 1. Okay, so from the very basic, from the very first question, we are dealing with the ethers. Okay, just a second. In the very first question, we are dealing with the ethers. In the very first, it is basically chemical property of the ethers. So before going to it, we will be teaching that we will properly ask how do we prepare the ethers. Okay, so in very first approach, we will try to see that how we can prepare the ethers. So the very important process is Williamson synthesis. So in this part, how we can prepare the ethers? We have to take an alkyl halide. And along with it, we have to take a oxide, or we can say that alkyl oxide. So if we take an alkyl oxide, RO minus, in the presence of dry ether, it will show an SN2 reaction. What will it show? It will attack at this position, leaving behind the halogens and yielding ROR. This is the ether. And now what we have to do? We have to do the chemical reactions or the reactions to be followed by these ethers. So chemically, this ether is very inert. And how can we proceed with the reactions of this? Simply, we have to take those species which we can activate these ethers using. We can firstly go with acids. Okay, what it can show? The lone pair of this oxygen will attack at this position, and what will the product be? RORH plus. And now this is a reactive species. Now what will be happen? Imagine we are taking H positive from HCl. The H positive is already utilized, and the Cl negative will act as a nucleophile to attack it. So it can attack, this is negative, this is positive, it can attack over this, leaving behind this species again, and you will get ROH along with RCl. Mind it? And always remember, this reaction is not always SN2. It depends upon the substrate which you are using. Okay, imagine, let us say you have a substrate like this, CH3, oxygen and CH3. Let us say you have in this ether, and you are reacting with HI. What are the major products that will be formed? We will discuss it now. Let us see. You are having this reactive oxygen because of the presence of the lone pair. It can attack at this position, taking an H positive, taking a proton from it. So you will get CH3 again, methyl, and OH positive and CH3. And now you are having I negative. Now most of the students have the doubt that where does this I minus go? It have the two possibilities. It can either go at this position and either go at this position. But the major crux over here is that it will go to the position that most of you have gone through, that it can show an SN2 reaction. But you are wrong here. What it can show, if there is a possibility of the formation of more stable carbocation, it will tend to show the more stable carbocation formation and will yielding this position apart. Let us say you are having this tertiary butyl anion. Let us say you are having CH3C, CH3 positive. And you can also see that this positive charge is stabilized by how many number of alpha hydrogen? The number of alpha hydrogens are 9 over here, which makes this carbocation extremely stable. So it will be the case, and next you will be getting one of the product CH3OH. Mind it. And now this I negative will attack over here, yielding CH3, CH3, CH3 and I. This is one of the product. Got it? Okay, and now what will be the case if you are taking one more molecule of HI? Always remember, you are taking the HI in one equivalent. You are taking HI in one equivalent. If equivalents are not mentioned, it means you have to take it in the excess. So what will you get? This CH3OH will again attack with H positive, HCl, HI, sorry. You will get CH3I. I hope this will be clear to you. Is it? Okay. Okay, let's back to the question part. What the question is suggesting. Okay, let us see. You are having this species, and in this species you are having the pH. If we will make an exact structure of it, you are having this pH O CH2 pH. See, and you are reacting it with HI. What will you get? If you react with HI, the lone pair will attack on H positive and yielding H and O positive. Okay, and after this, now you have two possibilities. From which position the molecule will remove, at which position the CO bond breakage will take place. And you have the two options. The first one is this, the A part, and the second one is this, B part. Can anyone suggest that which cleavage will take place, either A or B? Okay, we can see that, we can clearly observe that this bond cannot be broken from here. It can't be the case, because if this happens, you will get the phenyl carbocation like this, which is extremely unstable. Why is it so? You are giving the positive charge over the double bonds, and you will get a cleavage from A, not from B, yielding to the one of the product formation. What will it be? It will be this pH CH2, and this is OH. This is one of the product, okay? And the next product is, you are getting this CH2 positive. My bad. It's CH2 positive from here. And you will get PHOH. And now the I minus you have already taken, that this I minus will attack as a nucleophile to this carbocationic species, yielding CH2I. This is the final product. Okay, this is the final product. So it means we are getting the phenol as well as CH2I. The phenol and CH2I. This is the final answer of this question. I hope everyone is clear with this question. Aishwarya, can PHOPH react with HI? No, it can't be the case, because how will it be? Let us say you are having, just a second, if you are having, let me delete it for you, something. See, if you are having PHOPH, if the H positive will attack over this position, it will form like this. And now it doesn't have any chances for the cleavage of the bonds. It can't be cleaved, because if it cleave, it will get a positive charge over the benzene position. And it can never be the case. It is most destabilized position. Okay? I hope, Aishwarya, it clears your doubt. Okay, let us move to the next question or next concept we are dealing with. Okay. Yes, we are given the two statements. The first one is orthonitrophenols can be separated by same distillation. Before going to this question, we will discuss some methods, or we can discuss which are the physical properties that they are dealing with. Okay, let us see. We should know that what is orthonitrophenol and what is paranitrophenol. Let us see. You are having OH and this is N O double bond O. This is orthonitrophenol. This is orthonitrophenol. And if we discuss about the paranitrophenol, this is paranitrophenol. What is the difference between them? There is a major difference that this OH, if I can write it like in the form that this H will interact with this, yielding in hydrogen bonding. So what will you get? You will get an intramolecular hydrogen bonding in this case. Intramolecular hydrogen bonding. And in this case, you are getting the intermolecular hydrogen bonding. Intermolecular hydrogen bonding. How it can show the intermolecular hydrogen bonding? The other molecule of the same compound will interact with it. Okay? The other molecule of the same compound will interact with it. Now, this O will interact with the OH position of other molecule, yielding an intramolecular compound. And we all know that due to the intramolecular interactions, it will exist in like a discrete molecules. It means the boiling point of orthonitrophenol is comparatively very less as compared to paranitrophenol, yielding, we can say that this orthonitrophenol is steam volatile. क्या बोल सकते हैं हम? We can say that they can be separated by a method steam distillations. Okay, so which makes the orthonitrophenol can be separated by steam distillation. Yes, they can be separated by steam distillation based on the boiling point difference. Okay, let us move to the next statement. What does it suggest? The orthonitrophenol forms intramolecular hydrogen bonding. Yes, it can show, while the paranitrophenol can show intermolecular hydrogen bonding. This statement is absolutely correct, which makes both the statements statement 1 and statement 2 absolutely correct. Okay, is it? So let us say that both the statements are correct. Okay. So let us move to the one very important question which may be asked in your exams. Let us say, if I can ask you that what will be the acidity order? The acidity order of ortho, meta and para orthonitроphenols. Can anyone give the answer to this question? That which one is more acidic? Is it ortho, is it meta, or is it para? This is very important question. It can be asked in your exam. Okay, let me give you 2 more minutes to answer this question. Meanwhile, we will discuss the doubts which you are asking in the comment section. Okay, Shreya is asking इटार्ड reaction बता दीजिए, इससे confusion होता है. Shreya, you can go to my previous class that been asked and that will be done earlier. I have clearly discussed the complete ITARD reaction regarding the same. I hope this can't be your confusion again. Okay, let us make some structures to more clarify it. What is the acidity order? Let us say you are having same orthonitrophenols. It means OH is there and NO2 is here. Okay, and for the meta, this is OH. We all know this position is meta position. This is NO2. We can write it like this. and this is para. This is para, this is meta, and this is ortho. And you have to go with the pK values. The Aishwarya has given the perfect answers that all these type of questions you need to go with the pK values. And the para is absolutely a correct answer. The para is having the most, if we compare the Ka values, the para is having the most Ka, it means it is most acidic. And then the ortho, then meta. I hope you can learn it by this concept. Okay, I can give you the some more question that what is the common name of this compound? If I can ask you, what is the common name of this compound? This is a very important and very basic question, that what is the common name of this? All of you are much aware that what is the IUPAC name of this compound, but I want you to please give me a common name of this compound. Anyone? Yes, Aishwarya, you are right. It's because of that concept. Anyone? Okay, let's back to the move. This is picric acid. This is actually an alcohol, but it can act like an acid. It is very much acidic in nature. That's perfect. This is picric acid. Shall us move to the next part? Yes. Okay. Now we are given with some kind of hydrocarbons, and we have to do a reductive ozonolysis of this. Let us go in the depth of this question, what has been asked. Okay. In this question, you are given and in the very first approach, you must aware that alkenes are of mostly three types. We can say that. The first one is isolated. The second one is conjugated. And the third one is cumulated. The third one is cumulative. And you all are aware that isolated means that two alkenes are not being any kind of conjugation. It means there is no interaction in between them. And as far as we know, the conjugation means they are moving like this, this, and this is are in complete conjugation. And for the cumulative, you can also say that they are allenes. You can say that they are allenes, and they are like this. It means both the double bonds are present at only one carbon. Okay. So this is allene. This is cumulated allene. So let us discuss the ozonolysis of this allene. Okay. I will give you the most simplest approach to deal with this question. But before this, you should know the concept as well as the mechanical approach for that question. Let us discuss first the mechanical approach. Then I will give you a simplest approach to do the ozonolysis. Either it is reductive ozonolysis or it can be oxidative ozonolysis. Let us discuss the same first. Okay. For the first, if you are given an alkene, let us say I haven't taken this alkene, and you are reacting it with ozone. You are reacting it with ozone. What will be the case? There, it leads to the formation of RCOC. Here it is H, and this is C. It's H already here. it's H and CH3. This is the intermediate which will be formed during the process of the ozonolysis. Okay, and then if you are reacting it with zinc, what will it go? It will carry, including the water, what will it can do? The zinc will take up this oxygen and the bonds will rearrange itself. That this bond will shift to this and this will move here and leaving the oxygen with zinc, yielding what will it go? That becomes R, C, double bond O, H, along with its CH3, C, C. Let us say you are having CH3, C, double bond O, and H over here. It's only C here. It's H and CH3. Okay, this is the case, and you are getting the products over here. This is kind of reductive ozonolysis. What will be the case if I can carry out this H2O2 in spite of H2O? What will be the case? What will happen? It will do and act like an oxidizing agent. It will oxidize the already present aldehyde in the solution to the carboxylic acid, and it will yield the formation of R, C double bond O, OH, yielding this aldehyde to get into the carboxylic acid, and also this, that CH3, C double bond O, OH. These are the final products when you are taking H2O2 in spite of oxygen, in spite of water. I hope both the oxidative cleavage as well as the reductive cleavage is clear to you all. Shall we move to the cumulated part? Is this clear with you? Okay, let us move to the next part. So let us discuss the cumulated ozonolysis. What will it be say? You just need to go into the portion that if there is a presence of double bonds, just cleave that part. Just cleave it. And give the oxygen to both the positions. Let us say you're having this. Just give the CH3, CH, and that you're breaking the double bonds. It means you are getting an oxygen over here. Also in case of the other bonds, like you're having this carbon, you're having double bond, just give the oxygen to it. You're giving oxygen and oxygen. And same for the case of this. You will be getting C double bond O, CH3, CH3. It means they are the product of this reaction. I hope this is clear to you all. And you are given the reductive ozonolysis, not the oxidative cleavage. Oxidative ozonolysis. If there will be the word that oxidative ozonolysis, you will have to carry out the reaction to ultimately lead the carboxylic acid if there is a formation of aldehyde over there. I hope this is clear to you all. Is it? So let us check which answer should be the most probable for this reaction. We are getting ethanol. The first one is ethanol, the second one is acetone, and the third one is carbon dioxide, which makes option 2 a correct answer. Is it? I hope everyone is clear with this portion. Shall us move to the next question or next concept? Okay, let us move to the next concept. And now you are having the most important part, the preparation of phenol. You can see clearly that this is cumene. We all are aware this is a very special reaction, and we are all aware that how this process can be followed and what could we do in this part of reaction. Let us discuss the mechanistical approach of this question. Okay, let us say you are having cumene. You are having the cumene, and you are reacting it with oxygen. You are reacting with it oxygen. So what will be the case? you are having the hydrogen, you are reacting it with oxygen. What will be the case? You are getting this oxygen to be added at this position, and you will get, see, here the CH3 is already present, CH3OOH. This is the intermediate which is formed over here, and we can say that this is cumene hydroperoxide. This is cumene hydroperoxide. And if you are reacting it with, let us say, an acidic hydrolysis, what will be the case? You are reacting it with H plus and water. If we get into the mechanistical approach, what can it be? Let us discuss a minute aperture of that. Let us say there are the two oxygens which can react with the acids. So let us say it is going to react with this H plus. And what will it can be? It will form, here the CH3 is already present, CH3OOH, and it can take a proton, and now the lone pairs of this oxygen will migrate over here, moving back this position to get into here and leaving the water molecule aside. Oh, sorry, moving to the, just a second. This will shift to this position and move this to this, and you will get CH3 double bond O, the one of the product, the acetone, along with a phenol. This is the preparation of phenol, and you are getting the acetone as a side product, or we can say that this is also a product along with the preparation of phenol. Is it? I hope this is clear to you all. Let us check which option and what the question suggests. You are reacting with this ozone and you identify the compound A. It means we have to deal with A. And the A, we have already discussed that there will be the formation of OOH replacing the H, and we will be getting option 2 as a correct answer. Is it? No, Ishwari, it can't be the case. The para, then ortho, then meta. Along with the ortho effect, the other factors can be involved in that process. So we will be not getting into the depth of the portion, but you can get into the pK values that will be more suitable to carry out the acidity order. Okay. And Monica Goyal, sir, please explain the previous question again. Which one? It means you are confused in this question, isn't it? This is the most easiest concept that you don't need to get into the mechanical approach. You can simply solve this question. Exactly. Yes, Sheetal, you have given the perfect answer. But in this question, what you can do, you can simply break the double bonds. And if you are breaking the double bond, if this is the carbon and this is the carbon, and you are getting this double bond, just break that bond, and give the oxygen to everyone. Is it? And you are getting the products. Is it? I hope, Monica, you will get the answer. Do you want me to get into the mechanical approach again? Okay, let us move to the next question. If Monica has some more doubts to what is the major concern in that question, we will discuss that part again later. Okay, let us move to the next concept. What the next question is asking from us. Okay, now we have a question number 79. And I can clearly see that this is a physical property. This is the question of the aldehyde and ketones, specifically from the physical properties. So, shall we discuss the physical properties of the aldehyde and ketones in the depth of the portion? That no other option, no other question is lagging behind. So, let us discuss every physical property of the aldehyde and ketones. Let us see the first portion. It means if you are having the methanol, it is always gaseous at room temperature. It is a gas at room temperature. Can anyone suggest if we are dealing with ethanol, what will be the case? Is it a gas, liquid or solid? Can anyone will tell me? Ethanol, you have already used in your labs that it is a volatile liquid. It is a volatile liquid. And the higher sequence, the propanol, butanol, they are liquid or they can be solids. Okay. The others are liquid or solids. No need to get into the detail of the physical properties. Okay. I hope this is clear. On moving to the next point, that the lower, if we are dealing with a boiling point, if we are dealing with a boiling point of aldehyde and ketones, if let us say you are having an aldehyde or you are having a ketone, you can clearly see that there is a polar bond in between them. If there is a polar bond, so there will be a dipole-dipole interaction. If there is a dipole-dipole interaction, it means they are having the more boiling point as compared to hydrocarbons or ethers of same molecular formula, of comparable molecular formula. Is it? So the boiling point is greater than hydrocarbon or ethers. This is always the case. Because of, they might ask you what is the reason that the aldehyde or ketones are having the higher boiling point as compared to aldehyde or hydrocarbons or ether. It is just because of dipole-dipole interaction. I hope this point is clear to you. Is it? Okay. Let me ask you something more. That just a second. What will be the case? If you are having the propanol or butanol, so which is having A or B, which is having the greater boiling point? Can anyone give me the answer of this question? You are having the A, this is propanol, and you are having the B, which is butanol, which is having the greater boiling point. And how can we justify it? Can anyone know it? Or shall we proceed? Okay. You are having A or B, that this is a propanol. It means you are having the lesser molecular mass as compared to B, which is butanol. As we move to the more carbons or more molecular weight, it will increase the van der Waals forces of interaction. If it increases the van der Waals forces of attraction, it means the boiling point also increases. Okay, if the boiling point increases, it means, or you can say that they are hydrophobic as well because the number of carbon atoms are increasing. Yes, Shwarya, you are perfectly correct. Okay, let us move to the question part. What the question suggests? The methanol is a liquid at room temperature. Absolutely wrong statement. Because we have already studied that methanol at room temperature is not liquid, it's gas. It's gaseous in nature. And if we move to the next point, the boiling point of acetone is more than propanol. The boiling point yes, you can clearly see this is having the more boiling point. This is clearly mentioned in your NCERT. This is clearly mentioned in your NCERT that acetone is having the more boiling point as compared to propanol. Is it? Okay. On moving to the next part, the boiling points of aldehyde and ketones are higher than hydrocarbons or of comparable molecular formula. We have already discussed that this point is absolutely correct, and it is just because of higher will be the dipole-dipole interactions in case of aldehyde and ketones. And this will not be the case in case of ethers as well as hydrocarbons. I hope this is clear to you all, which makes the B and C, the option 2, a correct statement. Correct answer of your question. Okay, so let me discuss some more points regarding to the physical properties, that the lower mass, or we can say that lower aldehyde or ketones are more soluble, in water. As the molecular mass increases, the solubility of these compounds in water decreases. And also, the aldehyde and ketones are soluble in organic solvents also. And always remember a clearly distinguished point, that the lower members, in terms of smell, they are pungent. And as we move to the higher members, they are fragrant. I hope this is clear to you all. And this is because the higher member of aldehyde and ketones are usually used in your perfumes bottle. I hope this is clear to you. Shall us move to the next part? Okay, let us move to the next part of this question. Okay. This is very interesting question, and this is I can clearly see that this question is from haloform degradation reaction. This is haloform degradation reaction. We will discuss the mechanistical approach as well, and we will discuss how to get into the answers very quickly. Okay. I will give you just 2 more minutes to solve this question so that you can answer me what is your answer. Then we will discuss the mechanistical approach of this question. Okay, let us move to what the question suggests and what is the mechanistical approach regarding it. Okay. Let us move. You are having this. You are having amide. And you are reacting it with base in the presence of Br2. So what will be the case? What will be the intermediate which is going to be asked? So let us discuss everything in detail. Let us say this is base, this is positive, this is negative, and this is amide. We can write it like in the form that this is hydrogen. This base will abstract a proton from this amide, yielding an H minus, and we are giving you a bromine. We can write it like in a form like this, and this negative will attack over this and remove this Br negative. And remove this Br negative. What will you get? You will getting C double bond N H and Br. And again, in the case that you are having the KOH in excess come out, so this again KOH, this OH will again abstract this proton. You will be getting N minus Br. And now the main step occurs, the rearrangement step. In this part, this negative charge will go at this position, and the phenyl ring will migrate to this and removing this bromine. And what will you get? You are getting N double bond C. If this negative charge comes here, it will form a double bond with carbon, and the carbon is also having the oxygen with it. This is isocyanate. This is isocyanate. We can clearly write it. This is isocyanate. This can be asked that what is the intermediate that can be formed in the Hofmann degradation reactions. Okay. So after this, what will be the case? You are having the isocyanate. You are reacting it with water, and you will be getting, if this will be the case, then this water, you can clearly go in with the simplest approach, that this bond will cleave, these two double bonds will cleave, the two hydrogens will get to the nitrogen, and you are getting NH2 along with CO2 that can be released out. And you can clearly see you will get aniline. You will be getting aniline. I hope this is clear to you. And we can say that you are having, let us say, you are having this compound, and there is a presence of CO group. Hofmann degradation. Degradation means there is a removal of one carbon, or it will degrade itself. And how it can be? Because of this method. Now you can clearly see that there will be the removal of CO from this group, and you will be getting benzene attached to NH2. We can clearly say that this is aniline. Is this mechanical approach? Okay. You are getting the aniline as a product. And if we go to the sequence part, you have already attained the A, and now you are reacting with CHCl3 along with KOH. This is again a reaction, a very important reaction, that you are reacting the aniline, with CHCl3 in the presence of KOH. This is very, very important reaction. And in this chapter, exactly, and in this chapter you have already gone through with the Reimer-Tiemann reaction. In that reaction, we are using the same, this compound. This reagent is same in the Reimer-Tiemann reaction also. Is it? So let us discuss this mechanical approach in very much detail, so that you can get each and every point, that why is it happen, why will it not be go at the ortho position, why not meta, why not ortho, why will the nitrogen will only attack. So let us discuss each and everything in very much detailed portion, so that you can attempt this question in your NEET examination. Okay, let us move. You are having the CHCl3 and with base OH minus. The first and foremost thing in this reaction, what will be? It will abstract this proton. It will abstract this proton, yielding CCl3 minus. It will yield CCl3 minus, same like in the case of Reimer-Tiemann reaction that we are going to discuss later on. Okay, and after this, to stabilize itself, it will form CCl2 radical along with Cl negative. And now this will act as an electrophile, and this will act as an nucleophile, and this is simply an electrophile nucleophilic reaction. Okay, we will be going into very much detail in this part, that you are having this, and now the lone pair of this position, the lone pair of this nitrogen will attack to this electrophile. What will you get? You are getting the N, it's H, H, C, Cl, Cl, it's positive and it's negative. Is it? And that negative will abstract the proton. We can say that intramolecular hydrogen shift. You will get the nitrogen C, Cl, Cl, hydrogen, and this is only one hydrogen. And the lone pair will also activate itself, leaving behind the Cl apart. You will get N, H positive, C, H, Cl double bond. You will get a double bond, and the Cl negative that is relieved will abstract this proton, giving you what? N double bond C, H, Cl. And now again will be the case that the lone pair of the nitrogen will again move to this position and leaving the Cl negative again. And you are getting your final product. And triple bond C, it's positive and it's hydrogen. And you are getting the Cl negative will abstract this proton, and the product will be the same. And triple bond C minus, it's plus. You are getting the isocyanide as a major product in this sequence of reactions. In this, the very first, after the Hofmann bromamide, you are getting the isocyanate, then you are getting the isocyanide as a major product. I hope this is clear to you all. Is it? Okay, let us move to the next concept or next question. Okay. So what will be the question suggest? The product obtained when acetaldehyde reacts with semicarbazide. Most of you are not aware that what does this word means. What is it? Is it? Most of you are not aware of this term. That what is semicarbazide? So let us discuss these terms in detail so that each of you can give the perfect answers. Let us see. If you are reacting, let us say you are having the aldehyde. Let us say you are having the aldehyde, and we are reacting it with, let us say, RNH2. Let us see, we are replacing it with Z. We are replacing it with Z, and any substitution it can be. So the lone pair of this nitrogen will go to this. The lone pair of this will attack at this position. And why will it be? Because this center is electrophilic in nature and this nitrogen is nucleophilic in nature. So we can clearly say that this is nucleophilic addition. This is nucleophilic addition. You are getting O minus, the hydrogen is already present, and N, H, H, Z positive will be the case, and now this negative will abstract this, and you are getting OH, N, Z, H. This will be the case, and you are all aware that at a single carbon there will never be the case that two other functional groups are present. So one will have to remove itself. So the lone pair of this nitrogen will come back at this position, leaving behind the OH. You will get this product. You will get this product as a final product. Or we can clearly say that this reaction is nucleophilic addition then elimination reaction. Is it? So let us discuss what can be the Z and why does the name changes and what is the approach to deal with. Okay, if you are reacting, let us say you are having the aldehyde and you are reacting with ammonia. This is ammonia. You are getting an amine. You are getting amine. How does the structure look like? It will look like the hydrogen double bond NH2. This is amine. This is amine. And if we are replacing this ammonia, we are replacing one hydrogen with NH2 with R. Let us say we are taking RNH2. So what will be the case? You are getting here H double bond NHR. This is also an amine, but this is substituted amine. Or we can say that this is Schiff base. This is Schiff base. I hope this is clear. Let us move to some more reagents which are reacting with it and you will be getting the products. Okay, let us say you are reacting again with NH2, NH2. You are reacting with it. It means it is a hydrazine. So how we can proceed the reaction? That these two hydrogen will remove an oxygen from it, yielding this is hydrogen double bond NH2. This is hydrazine, and you are getting this. This is hydrazone. This is hydrazone. Is it clear? On moving to this, if we remove this NH2 with, we can write it like OH. This is hydroxylamine. This is hydroxylamine. You are getting, this is hydrogen again, this is N. These two hydrogen along with one oxygen, you are getting OH. This is oxime. It is oxime. I hope this is clear. Let us discuss some more reagents reacting with an aldehyde. Let us see. If you're having this is hydrazine, we have already discussed it about it, but if I can replace one hydrogen, if I replace one hydrogen of this and will put a phenyl over this, you are getting phenyl hydrazine. This is phenyl hydrazine, and you will be getting two hydrogens, one oxygen. You will be getting R, H double bond N, NH, PH. This is phenyl hydrazone. You will be getting phenyl hydrazone, and you guys are already aware that the aldehyde, you have a reaction called 2,4-dinitrophenyl hydrazine reaction, or we can say that 2,4-DNP test. I hope this is, you have reminded this. The 2,4-DNP means you are replacing this position NH2, NH, you are having the phenyl over there, and your 2,4-dinitro, it means this is the second position. Writing the NO2 over here, this is 2,4-DNP. 2,4-DNP, and you are reacting with, you will be getting 2,4-dinitrophenyl hydrazone. You are getting 2,4-dinitrophenyl hydrazone. Let us move to the semi-carbazide portion so that it can be more clear to you. You are having, let us say, this is the reaction. Acetaldehyde means CH3, C double bond OH, semi-carbazide. It means you have to take NH2, NH, C double bond O and H2. This is semicarbazide. This is semicarbazide. This is semicarbazide. And if you're reacting it with acetaldehyde, there are the presence of 2 hydrogen and 1 oxygen, you will be getting CH3 hydrogen double bond N, NH, C double bond NH2, semicarbazone. This is the final product. You can expect it from this reaction. So let us check which option clearly suggests this option. This is CH3, CH, N, NHC double bond, or CH3. This is clearly a perfect answer. I hope this is clear to you all. Is it? Okay. So we will discuss the rest of the questions. For if you guys have any kind of doubts, I am here to discuss with you. Apart from it, we will meet you in the next session. So thank you very much for joining this class.